Hello, everyone. Today I'm going to give an introduction to SenseAI, or Sensei for short. Sensei is a spin-out company from the University of Liverpool, where it is focusing on the use of compressive sensing for all types of imaging applications. One of the areas that we're focusing on at the moment is in electron microscopy, where by acquiring a smaller number of pixels in our image and using a form of compressed sensing called in-painting, we can recover the full image for much lower dose and much quicker. So just to give an example of how the approach works, let's start off by talking about sparse sampling. So sparse sampling is pretty much the way that it sounds. Typically, when we're doing a scanned image, we do a raster scan, which is much like a word processor works. We type all the way across to the right-hand side, and then we flip back to the beginning, one line below. Now, if we want to randomize this scan, we can do what we've got in the middle, and so we can have a random scan instead of a raster scan. If we want to subsample that random scan, you can see on the third in C, we have an example of a random scan. And then because we have hysteresis in an electron microscope, we have to do an implementation of the random scan, which we call line hop. And that line hop basically allows us to do a random walk and to get a randomized subsample scan of the image. So our goal is to apply or acquire as few pixels as possible, and that speeds up the image. But to make it practical, we also have to be able to get our reconstruction of the full image as quickly as possible. And what we're aiming for is to have a video rate reconstruction so that when you acquire a sparse sampled image and you do compressive sensing and in-painting, you get an image in the same time as you would normally get a full scan. So let's talk a little bit about the reconstruction. So here's an example of something you might see in a basics physics class or electrical engineering or signal processing class. We have a complex waveform on the right, and that complex waveform is made up of the dictionary elements that we have on the left. And these are just sines and cosines. And in the terminology of compressive sensing or dictionary learning for compressive sensing, those sines and cosines are the dictionary elements. Now, if we know what the dictionary elements are, we can actually get rid of a lot of the signal in our complex image or our complex structure and effectively still reconstruct the image very accurately. And we can get down, it's only when we get to about a few percent of the signal that we start to have small differences in our reconstruction. So what this is telling us is that effectively, if we know what the dictionary elements are, we can reduce the amount of signal we need to acquire, and we can get an accurate reconstruction. Now, in this case, there's no compressive sensing or artificial intelligence involved in the process. We know what the dictionary elements are, and so we can go ahead and reconstruct the signal. In the images that I'm going to show from the electron microscope, the AI comes in because we don't know what the dictionary elements are up front, and we don't know what the complex signal is, and so we have to solve together to get those to work. And we use a process or an algorithm called BPFA, or beta process factor analysis, and that allows us to get this process moved forward for solving an image when you don't know the dictionary up front. So what we have to do is to figure out what the dictionary is. Now, the process that we use is to start from something like a wavelet or a standard dictionary elements that allows us to reconstruct the image, and then to modify that based on the structure in the image, and that's what you get with the BPFA output. So effectively, what we've done with Sensei is to focus on how do we apply the dictionary to allow us to get our quick reconstructions. And this is the key to doing the compressive sensing. We have to be able to do it quickly and efficiently through either learning the dictionary or transferring the dictionary from another part to be able to interpret the image. So here's an example of a reconstruction of a live image. This is an aberration-corrected STEM image that's obtained from Harwell in the Rosalind Franklin Institute, and it's just silicon dumbbells. And you can see that we can get a very rapid reconstruction. So this is a live reconstruction of a 25% subsampled image. Now, because we're learning the dictionary from each individual image, we're getting to the point where we don't have to do learning like you normally do with artificial intelligence. That means we can change the focus, we can change the magnification, and we can still reconstruct the image very accurately. Because we're not doing a machine learning or a deep learning approach to reconstructing the image, it also means we're not subject to hallucinations. If we can't get the information across, you'll just see a blurry space where there's not enough information to get the reconstruction. The other part of this, of course, is that once we've reconstructed our full image, that means you can do all of the other methods for image processing at the same time after you've got your full image. Effectively, the approach that we've developed with Sensei is to reconstruct from a subsampled image into a full image. After that, you can do whatever you want to the image. So it also works for doing 4D STEM experiments. And so here we have an example of a 4D STEM experiment. You can see the detector on the left-hand side, the subsampling of the image of gold nanoparticles. And again, in this case, it's a Z-contrast image, but you can see a live reconstruction of the image. Now, the advantage of this for doing 4D STEM experiments, whether you want to do tychography, IDPC, or any 4D STEM experiment, is that by getting a live reconstruction while you're on the microscope, and this is the scan as it's progressing, we can change the focus, we can change the area, we can change the location, we can optimize to get the best image, and then we can acquire the full image after that. And that means it's much more practical to be able to do 4D STEM imaging in a microscope when you can see what's actually happening in the system as it takes place. Now, another advantage of using our dictionary is that we can also do image correction. So what we have here are two sets of images. At the top, it's a live image being acquired from the silicon dumbbells again, learning the dictionary and doing a reconstruction. And if you zoom in and you look at on the right, you can see there's a slight misorientation in the sample, there's a slight astigmatism, and we're not resolving the silicon dumbbells in that case. At the bottom, what we've done is take a simulation of the silicon dumbbells that you would expect under the imaging conditions of the microscope. And in this case, we're not subject to the signal to noise, we get a high quality image. And if you now do the reconstruction of your image, you actually get back to getting your silicon dumbbells. So effectively, by using the dictionary while we're working on the microscope, and I'll show in a minute what we can do after we finish on the microscope, you can correct for minor errors in the alignment or the acquisition of your images in the microscope. Another bit that we can do with the transfer of the dictionary is that when we're doing electron microscopy, we can get multiple signals simultaneously. So in this case, what we've got in an SEM image is a backscattered electron image at the top, very high signal to noise, large cross sections, great images that come out. We can get our dictionary, but then that dictionary we can apply to an EDS map. So in this case, this is the aluminium edge for the aluminium peak from the EDS map. And using the dictionary from the backscattered electron image, we can reconstruct that map and get something which is a lot higher resolution in terms of what we can see. So effectively, by using the dictionary transfer that was developed by Sensei, we can take these low signals and we can get a much higher quality image for the same amount of time and acquisition process. Now, the other things that we can do with this is that after we've got the images, and you may have noticed in those images that I was showing at Coming Live, they're a little bit blurry. And the reason they're a little bit blurry is that effectively what we're doing is we're running the reconstruction at the stage where we're trying to get speed. But after we've acquired the image, we can then process or reprocess the images and focus on getting the highest spatial resolution out of it. And because the images are always the same, they're using the same dictionaries, we can actually get a much better reconstruction that comes out. So here is an example of that. We have a 25% reconstruction again, using those those gold nanoparticles that we were looking at. We can separate the dictionary elements out from the background to the particles, and then we can recombine the dictionary elements together again, and this time focusing on taking the whole thing through to convergence, and focusing on the high resolution information that comes out. And you can see you get very, very high resolution information from those gold nanoparticles, and you can even see the individual gold atoms that are sitting in between the two nanoparticles. Now, the implementation of SenseAI is very straightforward. Essentially, we can plug our control software either directly into the scan generator in the microscope, if the scan generator is advanced enough, or we can use an external scan generator and just plug through this external generator into the external port on any microscope, and then off you go. It's basically plug and play, and then the system will allow you to get your subsampled images. So with that, thank you for your attention. Here is the contact information if you want to learn more about SenseAI, and thank you very much.